So what I'm trying to calculate here, again, is the integral from 0 to infinity of the sine function in x dx. So the first thing I do is I set up my limit. I introduce a new variable t. I'm going to integrate from 0 to t sine of x dx. T is just some real number. This lets me do the fundamental theorem of calculus. And I know my antiderivative is minus the cosine of x. Just like I was hinting, all I have to do is evaluate at the points x equals t and x equals 0. So I'm taking the limit of 1 minus the cosine of t. And so the oscillating that we were seeing before, where just the painting the area and measuring that was oscillating between 0 and 2. And the reason for that is right here. It's this cosine function. The cosine function is going to bounce back and forth between -1 and +1. So that's going to give us between 0 and 2 for the amount of area that we've painted. But as t goes to infinity, the cosine function doesn't settle on a limit. So this improper integral diverges. There is not a value we can give it for the net area that we have painted. As a side note, I'm going to return to my graph. And let me pick some more sensible bounds. Let's go x up to 200 now. And I'm going to make my b a slider again. There we are. The problem with integrating the sine function is that on top of the x-axis, I have infinitely many of these humps which all have 2 units of positive area. Below the x-axis, I have infinitely many of these humps which have 2 units of negative area. And there's not a sensible way I can assign a value to infinity minus infinity. So for that reason, the integral diverges. Now I'm going to change things slightly here. First off, I'm going to start my integral at 1 for technical reasons, but I'm going to make it so that the humps of my function are actually going to shrink as I go. So I'm going to change this formula and say that I'm integrating the sine of x divided by x. So we tried integrating 1 divided by x before. That didn't work out too well. Let's try sine of x divided by x. So you can see in the picture that each of the humps is getting smaller and smaller as I go out on the x-axis. So I'm painting the blue area positive, I'm painting the red area negative. And as I go, look what happens on my numerical readout here. For the smallest b I can consider is b equals 1. The integral will be 0. But as I go out, this looks like it's approaching a limit. It looks like I get 0.62 and change. Now, why would that be? Why would this limit exist? If I was going to calculate this on paper, I'd need the antiderivative for the sine of x divided by x. And while that is a function, the calculation of that function is not something that we're going to do in Calculus 2. We just need to know it exists. So if you're interested, you can read about it. It's called the sine integral function because it's the integral of sine of t divided by t. But I need to explain why this limit exists without using an antiderivative. So think back to limits, we know that limits will exist because as the further I go out, my value for this integral is settling down. As I paint more of the x-axis, I have a blue area which adds a bit. I have a red area which subtracts. I have a blue area which adds a little bit less. And then I have a red area which subtracts even a little bit less than that. And I have a blue area which adds a little bit more again. And I have a red area which subtracts a little bit less again. So the value of this function is swinging up and down depending on if I'm in a red region or a blue region. But the amount it swings by is shrinking every single time. So the farther I go out, the less and less this is moving around. Now, just to return to my slides, if I was going to calculate this, I say I have this improper integral. I'm integrating the sine of x divided by x dx. So I set up my limit. I want the limit as t goes to infinity from 0 to t, integrating sine of x divided by x dx. And what I was just saying is this function does have an antiderivative. It's one that's complicated enough that we won't be worrying about the actual formula of that antiderivative for this class. And I claim, this does take some grunt work that I'm not going to be doing in this talk. If you integrate starting at 0 and going up to t, then you'll get exactly pi divided by 2. That is the net area. So if you painted all of the blue above the x-axis and all of the red below the x-axis, there would be pi over 2 units of area more on the blue side. That's one way to think about this. And again, we need to be careful here because it's the limit that lets me make sense out of that idea. So we can calculate improper integrals, integrals that don't let us do fundamental theorem of calculus, by remembering that limits exist and thinking about taking the limit of quote unquote proper integrals.